So in section 2.7 and 2.8, we talked about a derivative being the instantaneous rate of change. That instantaneous rate of change is the slope of the tangent line, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. And we ended section 2.7 and 2.8 by using the limit definition of a first derivative to calculate the first derivative. Now in section 3.1, we are going to be going through the shortcut for finding the derivative of polynomials and exponential functions. So you no longer, after today, have to use that full limit definition. You just have to recognize the limit definition, and we'll talk about it more as we go. So just some rules with finding the derivative. A derivative is the instantaneous rate of change. Anytime that you're finding the derivative, you're going to be using this idea, you have to go down, okay? So we're going to be going down. So for example, in section 2.7 and 2.8, we talked about how we went from a cubic, the derivative was a quadratic, and the derivative of that was linear. So our exponents slowly go down. So to start with, we have the derivative, so d over dx. That means we're actually finding the derivative of a constant. The derivative of a constant is 0. A constant multiple rule, we're taking the derivative of a constant multiplied by a function. You're simply going to drop down the constant, and you're going to multiply it by the derivative of the function. Whenever you see addition in between two functions, you're going to separately find the derivative. And when you see subtraction in between two functions, you're going to separately find the derivative of each. Now, the main rule for functions is the power rule. So we have x raised to the power of n. Every single time that you see x to the power of n, x has to be in the numerator in order to do this. You're going to take the n, multiply to the front, and then you're going to subtract 1. So let's go ahead and do it. So we're going to find the derivative of number 1. In order to find the derivative, you're going to, first of all, write correct notation. So you have to write f prime of x. This means that I'm finding the first derivative. And you're simply going to take the exponent, multiply it by the 2, and subtract 1. Then you're going to do it again. Multiply the exponent by the constant in the front, subtract 1. When we take the derivative of 3x, again, you're going to think about there's a 1 right there. 3 times 1 is 3. And when we subtract 1, we get x to the power of 0. Anything to the power of 0 is just 1. So x to the power of 0 is 1. So it's really just 3 times 1, which then I don't have to put anything else. And then when we take the derivative of a constant, it's just 0. So again, on the end, we don't have to put 0. We just know that the derivative of a constant is 0. And this right here is our final answer. We're going to go through the same process in number 2. So we're going to find the derivative. So we've got g prime of x equals. So I'm going to take the 4 and I'm going to multiply to the front. Subtract 1 and we get 3. Take the 2, multiply to the front. Subtract 1 and we get 1. Again, we don't have to put it. The derivative of x, the number next to x, is just 1. And then the derivative of a constant, negative 2, is just 0. So this is our final answer. For problem number 3, we're going to use our fraction rules and rearrange this. So we've got y equals, so we get to put x underneath each one and reduce it. So we've got y equals x squared minus 4x plus 1. And then we're going to go ahead and take the derivative of that. Now, y is a little bit different than f of x or g of x. Another notation that we could write to represent that we just took the derivative, we could say dy over dx equals. So this is one of our notations in the box on the front of your classwork packet. And we're going to go ahead and take the exponent, multiply it to the front, and subtract 1. Take the exponent, multiply it to the front, subtract 1. And then the derivative of a constant is just 0. So if you look back to the previous page, the easiest problem to do is number 11. When we take the derivative of f of x equals x cubed, we said that the answer was 3x squared. Take the 3, multiply to the front, it's 3, subtract 1, and we get 2, so 3x squared. So we no longer have to use this limit definition to find our answers to any of our problems. go ahead and try out numbers 4 and 5. As you do so, go ahead and pause the screen so that I don't give away the answer. And this is the end of like our quote unquote easier problems, 4 and 5, where we get -6 and then 2x plus 6. And number 6, notice that on the end right here, we have a little bit of an issue. So it's 3 over x squared and then 5 over x. Whenever you see this, you're going to have to change the actual function. So you've got f of x, h of x equals 6x to the 7th minus 4x to the 5th. X cannot be in the denominator, so you're going to bring it to the numerator by making the exponent negative. And then you can go ahead and go through the process of finding the derivative of h. So we've got multiply to the front, subtract 1, multiply to the front, subtract 1, multiply it to the front, subtract 1. Now that became 6x to the -3. And once again, multiply it to the front, +5, subtract 1, and you get -2. Keep in mind, and you don't actually have to write it, but this would really be 6 over x cubed. And this would really be 5 over x squared. So keep in mind that if you were asked to rewrite it, you would have to change it into its correct form with no negative exponents. In question number 7, this one doesn't have an exponent, so you're going to have to change your radical into an exponent. So we've got t to the power of 1/2. And then we can go ahead and find the derivative of, this is velocity. So we take the 1/2, multiply it to the front, but then we're going to subtract 1. Now it makes absolutely no sense to put -1 right here because it's a fraction. So I'm going to put -2 over 2 so that I can go ahead and subtract the numerator. When I subtract fractions, you need a common denominator. Then we get -1/2. Now, keep in mind that you can leave your answer like this, but you should know that this is the same as 1 over 2 and then square root of t. I accidentally changed that to v, so I'm going to change it back into t. Okay, number 8. We've got s of t equals the cube root of t squared. So I'm going to once again change this. So it says s of t equals t to the power of 2 is my above number, 3 is my below number. Now we're going to take the derivative of this. We're going to multiply the 2/3 to the front. So you've got 2/3 times 1, which is 2/3. And I'm subtract 1. So once again, it makes no sense to put 1 because we have a fraction. So we're going to put -3 over 3 to get t to the power of -1 over 3. And then keep in mind that this is the same as 2 over 3, and then it's the cube root of t. So those are equivalent to one another. Now, number 9 starts off pretty easy. So with number 9, we have this y. I'm going to take the derivative of y, dy over dx equals. So we're going to start by taking the 2/3 and multiplying it by the 3 and subtract 1. So -3 over 3 gets me -1 over 3. Now, this right here, -7 to the power of x, is a little bit different. So we're going to go ahead and go back up to the box where we have an exponential with a base of, in this case, we have the number 7. So a could be any number. And here's the process that you're going to do. To take the derivative of any exponential, you're going to start by rewriting it. And then you're going to multiply by natural log of whatever the base is. So it's a rewrite times natural log of the base. So the derivative of -7 to the power of x, you're going to rewrite it, -7 to the x, and then it's going to be natural log of the base, and that's your final answer. And you don't have to do anything else with this problem. The only thing you could possibly do is move this x to the -1/3 down to the denominator, so 2 over the cube root of x. But -7 to the x, natural log x, is the correct answer. Number 10, we have y equals e to the x, and that's one of our other rules up top. So we can go ahead and, because it's exponential with a base of e, so it starts with a rewrite. So we've got e to the x, and then you have natural log of the base, which the base is e. So if you know your rules for natural log or how to solve natural log of e is just 1. So you really have e to the x times, not natural log of e, it's e to the x times 1, which you don't actually need to write that. You don't need to put the times 1. So we just go ahead and say that it's exactly the same. E to the x, the derivative of e to the x is just e to the x. So in this number 10, we've got y equals e to the x, so the derivative of that, dy over dx, is just e to the x. Go ahead and try out numbers 11, 12, and 13. So anything exponential, rewrite natural log of the base. Rewrite natural log of the base. If it is x to the with an exponent, multiply to the front, subtract 1. And then, of course, the derivative of constant is 0. And that leads us to our last rule in the box, and that is taking the derivative of anything with a natural log. So let's go ahead and come on up here. So anytime that you are finding the derivative of natural log, it's going to be 1 over, and you're going to take whatever that is and rewrite it. So 1 over a rewrite, and then you're going to multiply by the derivative of whatever this is. So that's the derivative. So 1 over a rewrite multiplied by the derivative. That's how you take the derivative of natural log. So let's go ahead and, with number 14, find our answer. So we've got dy over dx equals, so whatever's next to the natural log, that's what you're using. So we're going to do 1 over, and then this is a rewrite. And then you're going to multiply by the derivative of 2x, which the derivative of 2x is just 2. You should notice that you can go ahead and cancel out the 2, so really our answer is 1 over x. Number 15, same concept. So the derivative is going to be 1 over, and whatever that is, you're going to simply do a rewrite multiplied by the derivative of that, which is 2t. Notice that we can go ahead and cancel out one of the t's in the bottom with the t in the numerator, so our final answer is 2 over t. And then number 16 right here kind of gets into our rules for natural log, but with natural log, we could separate this. So you've got y equals natural log of e minus natural log of x, which then you know that natural log of e is 1 minus natural log of x. And so really, when we take the derivative, we've got the derivative of the 1, which is 0, and then you've got minus, and then we've got 1 over a rewrite, 1 over a rewrite times the derivative of x, which is 1. So really our final answer for this problem is negative 1 over x. Great. After this, we just go ahead and use these rules to find our answer. So from now on, anytime that you see or recognize the limit definition of a first derivative, that's exactly what this is. We're going to go ahead and highlight it. We'll call it f of x. To evaluate this problem, you don't have to do anything except for find what f of x is, and then take the derivative of it. And that's our final answer, 3x squared, and that's all we have to do. 18 is another limit definition of a first derivative. So you're simply going to recognize what f of x is and find the derivative of that. So you've got f prime of x equals, that'll be 3x squared minus 10x plus 4. The derivative of a constant is 0. We end with these last questions, 19, 20, and 21 of this video, where they want us to evaluate the derivative at a certain value. So what you have to do is figure out that x is an actual number right here. So we've got x equals 3. And so anywhere I see a 3, I'm really going to replace the x with a 3. So recognize that the function is really 4x squared minus 3x take the derivative, and then plug in the 3.